Now, why at all we are going to study the properties of Laplace transform? We have seen some Laplace transforms for some standard functions. Now, it is not possible for us to calculate each and every function's Laplace transform and remember it so that we can take its inverse Laplace transform whenever necessary. Now, if we have some properties so that we can extend our spectrum of functions and we can easily remember them just by looking at the properties, then we will have more functions so that we can calculate their inverse Laplace transform. So let us say, let me just select a pen. So if let us say if you have function A and if you have function B, after taking the Laplace transforms and after computing, you get the final Laplace transform which is B. Now you need to calculate the inverse Laplace transform of B, but you do not know what exactly is the inverse Laplace of B. You have not seen function B, but you know the Laplace transform and inverse Laplace transform related to function A. And if A and B are related by certain rule, say differentiation, say integration, maybe multiplying A by T gives you B, maybe multiplying A by some constant gives you B, then it is possible for you to calculate the inverse Laplace transform for B as well. So basically, you knew the inverse Laplace for A, and now because of the properties that you are going to study, you also know the Laplace and inverse Laplace relations related to function B. So that is why these properties are important. Let us see the properties one by one. So the very first property is superposition property. According to this property, if you have function f1 of t whose Laplace transform is given by f1 of s and function f2 of t whose Laplace is capital F2 of s, then Laplace transform of the addition of these two functions or the addition of the functions in time domain gives you the Laplace transform addition in the frequency domain as well. This is the straightforward formula for addition as it looks, but this is not true for multiplication. Basically, Laplace transform of multiplication in time domain doesn't give you the multiplication of Laplace transforms of the individual functions. So basically, this works only for addition and subtraction, and hence it is known as superposition. So this is the important first property. Second property is known as shifting. Now what is shifting? Shifting is nothing but if you want to multiply a particular time domain function by e raised to minus at, if you multiply a time domain function by e raised to minus at, every s is replaced by s plus a. So basically, if you have the original, uh, the example is here, the Laplace transform of 1 is 1 by s. And now if you multiply 1 by e raised to minus at, so basically the original Laplace transform is going to change by just replacing s by s plus a. So the Laplace transform of e raised to minus at into 1 will be 1 upon s plus a. You can just check this particular property for any other known Laplace transform. So this is the example for it. Third property is scaling, wherein you are going to multiply time domain functions time t by a particular constant a. So whenever there is t, now there is at. Now the Laplace transform changes according to this rule. So whole Laplace transform is multiplied by 1 upon a, where a is the constant, and every s is replaced by s upon a, where a is that constant by which t is multiplied. For example, you have e raised to minus t's Laplace as 1 upon s plus a. Now if you decide that you need to multiply e raised to minus t's t by a, so now the new time domain function is e raised to minus at. So using this particular property, what we are going to do is we are going to use this particular same function, and every s, every, so this should be 1, this is not a, this should be 1. So every s is going to change as s upon a, and the whole function is going to be multiplied by 1 upon. So this actually gives you 1 upon s plus a. Alright. So this is the third property, which is known as scaling property. The next property is the differentiation property, wherein if a particular function f1 of t is multiplied by t raised to n, alright. So t raised to n is nothing but t power some integer n, and now the function changes according to this n. The original Laplace transform for the function f1 of t was capital F1 of s. Now the f1 of s changes as nth derivative with respect to s of f1 of s and multiplied by minus 1 raised to n. Alright, just take the example here. If the original function f of t was e raised to minus t, whose Laplace transform we know is 1 upon s plus 1, and if you multiply this by t, alright, if you multiply this by t, what we have to do is we have to differentiate this one time, right? N is equal to 1, so we have to differentiate Laplace transform of this by for one time, alright. So the differentiation of 1 upon s plus 1 gives you minus 1 upon s plus 1 bracket square, and then you have minus 1 raised to 1 multiplied to it. So it gives you minus 1 into minus 1, and hence you get positive 1 upon s plus 1 square. The next property gives you the integration rule. So here, if the original function is f1 of t and the Laplace is f1 of s, then if you divide f1 of t by t, then of course you are going to integrate the Laplace transform with respect to s. So in the above example, when you multiply by some t raised to n, you have to differentiate the Laplace transform for n times, and if you divide the original function by t, then you have to integrate the Laplace transform to get the new Laplace transform. Alright. The sixth property is the differentiation property. Alright. So if you know the Laplace transform for f of t, which is f of s, you can easily find out the Laplace transform of f dash of t, which is given by this rule. You can see it is s into f of s minus f of 0. This is nothing but the initial condition. Alright, so initial condition will be given. You can find it out by putting t equal to 0 in the original form, and so on. So once you get the Laplace transform of f dash of t, you can then find out the Laplace transform of f double dash of t. You just need to know the Laplace transform of some original function, and you can calculate the respective differentiations Laplace transform. The exact opposite rule is the seventh rule here, which says if you integrate the original function with respect to t, then we have to divide by s, right? In the previous property, we were differentiating the function and we were multiplying the f of s by s, but here we have to divide by s when the integration has been taken for the original function. Alright, so these are complementary rules 6 and 7. The next property, which is very simple property, or this is nothing but a proof or corollary, which says the initial and final value theorem. According to initial and final value theorem, limit of t tending to infinity in f of t, which is nothing but the final value of function f of t, small f of t, is given by limit s tends to 0, s into ss. Alright, because s is nothing but frequency. Alright, frequency has the dimensions of 1 upon t, or say 1 upon time. So when time tends to infinity, s tends to 0. Alright, this is how you can remember this. And when limit t tends to 0 f of t, you have limit s tends to infinity, because when 1 upon t and t goes to 0, s will go to infinity. Alright, but the only thing is you have to multiply the original function f of s by s. So basically, if you have to find out the final value of the function, or say initial value of the function taking limit, limits, but you do not know what are f of t's, but you know what are f of s, then you can still find out the final value and initial value of the function using these two rules. I think you have understood the basic properties of Laplace transform. I hope you will be able to calculate the inverse Laplace for many other functions now. I will meet you whenever you call me back again. Thank you so much.